Good evening. It's me again, Jean-Louis. I'm an amateur physicist. I've presented myself in previous lectures. This is gonna be my last lecture, actually. Uh, it's actually on, I've got like 40 papers where I dig into problems in physics on my ResearchGate site, which you see there. Out of these 40 papers, I packaged like 10 of them into what I call lectures, and it's a bit of a joke on Richard Feynman. I think Richard Feynman made a lot of jokes. Um, so now I'm making a joke on Richard Feynman, I guess, with these lectures on physics. So some of them are really indeed a sort of a rewrite of his lectures, the basic introductions on what quantum physics is all about. This one, the last one in the series, really the last one because I'm signing off, brings a lot of stuff together. And so that's why I thought, you put so much effort into these things. Why don't you make a quick PowerPoint and do some marketing for it, I would say. So that's what I do. The brand name is there. The Emperor has no clothes. I think there's a lot of mystification in quantum physics. I'm not sure why. I think academics have to make sure that there's puzzles that are not solved. Otherwise, they're out of a job. But I think there's a lot of stuff that in quantum mechanics puzzles, on what electrons and protons actually are, that you can very easily solve. And that's where I go with what I call a realist interpretation of quantum mechanics. So you might also call it a mechanical interpretation of quantum mechanics. And indeed, in many ways, I think I go back to the old guard, to Einstein, the earlier Bohr before he, Schrödinger for sure, Dirac, Lorentz, before sort of these young wolves took over and rephrased everything, which drove some people to madness. I mean, Ehrenfest committed suicide in Leiden, the successor to Lorentz. A lot of people ended up being a bit depressed. Oppenheimer himself, even John Stuart Bell, and the second and third generation, you can see people were very enthusiastic, but in the end they say like, well, a proton and an electron, maybe we should not do what we do, and that's to think of it as like some structureless thing, but maybe it has a structure. So that was the intuition behind everything I did. Um, it was a philosophical interest, I will admit that. I want to know what is true. We want to know what reality is about, the essence. I'm a prolific writer. I think writing is good, so that makes it clear. The last advice of Boltzmann is also sort of when you think you found truth, defend it to your last breath. That is not what I'm gonna do. I said I'm signing off. This is my last lecture. So let's get on with it. Um, so I'm gonna talk a little bit about everything in 7-8 slides. What is everything? Well, everything is electrons, protons. Their antimatter counterparts have a theory on dark matter as well, but I won't bother you with that. These electrons and protons, they come together in atoms, and they make up atomic systems. We have neutrons also. I think these are sort of a glue between protons. They're neutral. I think they consist of positive and negative charge. But so yeah, I'm gonna talk about electrons, protons, atoms or atomic systems that consist of these electrons and protons. And to start doing that, I'll talk about the basic model, which is what I call an oscillator model. You see this thing going up and down in one dimension there, a mass on a spring, And that's sort of the metaphor that, when you do a quantum course, a course in quantum mechanics, you'll see it's all about, oscillators, and you can get really complicated models. Why are they complicated? Because, stuff moves very fast. We think of a charge, which goes up and down, but an electron also goes sideways, left and right, and then goes back. So that makes it an orbit. So the problem a bit is that in my model, I really think that electrons and protons, the anomaly in the magnetic moment and all these kind of things, and the quantum scattering effect, it can all be explained by, electrons and protons have a structure, and that structure is that they are an oscillation of charge. It's a very small point-like charge, not with zero dimension, and it sort of whizzes around in an orbit. And that orbit can be modeled indeed by, thinking of it as an oscillator. That's a mathematical model. You really shouldn't think of, in the beginning I thought that sort of maybe there's some elasticity there of space-time, right? And maybe that K and that equation there, that's the oscillator equation, the force that drives a small mass, or a charge in this case, that force, if the spring gets stretched, there's a constant, it will go up, but the K, that models a sort of elasticity. This is not an elasticity of space-time, not at all. When you have a ring current, it will generate an electromagnetic field, and that's sort of the beauty of these models, is that the electromagnetic field that is generated by the current, the current that is a small point-like charge generates, it generates the electromagnetic field. It's also what keeps it going, and so that's the only mystery here, is that that's very special. We have sort of a very small perpetuum mobile. What was the difficulty originally in sort of modeling this is, most oscillator models, I did a course on EDX, are linear oscillations, and I think electrons, protons, a photon is a linear oscillation of an electromagnetic field factor that travels at light speed through space, through empty space, or through a field, as a disturbance in a field. But protons and electrons are orbital oscillations, I would say, charged oscillations, that charge that goes around and round and round. So you can work that out, but the equations are not so easy. I mean, if you take that equation is relativistically okay. The force is, the time rate of change of the momentum. And the momentum is, of course, the product of a velocity and a mass. But what we have here is actually, I said, this is basically a mass without mass model. The whole mass, the energy in the electron and the proton is basically, this point-like charge. The force acts on a charge, and the mass that is generated is it's a zero rest mass charge which zips around at the speed of light. So MMV is the mass that it gets. It's all relativistic mass. The rest mass is zero, and so the velocity is c. And so these equations that I put here, this is basically an equation that I got from a paper from I should quote him. What's his name? Dylan B. Clark. Yeah. Thesis on relativistic springs, 2011. It's very beautiful. He shows actually that when you allow for these oscillator models, but you want to do it relativistically correct, is you don't get nice equations of motions. You can't solve it analytically. The best thing you can do, and that's what we're doing in there, is sort of deriving some kind of energy conservation equation. I do that by, well, I would say look at my paper on how to do that. This is the equation. Basically, I multiply the both sides of that force equation by the velocity, which is the time derivative, the time derivative of the position vector, and then you see that you get an expression for the energy, which says basically the time derivative of the energy, dE divided by dt, is the energy has two parts. One is a potential energy term, kx squared divided by 2, and that's what you have in non-relativistic oscillators as well. And you have a kinetic energy term there, which is the Lorentz factor, 1 divided by the square root of 1 minus v squared over c squared times the mass times c squared. And so as the mass zips around, the potential and kinetic energy will sort of, it will slosh back and forth. It will not be constant. Now, the beauty of it is that if you think like, okay, that's in one dimension, what if we have like two oscillators working in tandem? A spring going up and down at the same time, a spring pulling a mass. I don't like the spring metaphor too much. I actually put there a radial engine because we can have like, two pistons or four pistons or three pistons. It doesn't matter. In a system like that, you will have, linear oscillators making stuff go round and round and round. And that actually gives then rise and solves my problem of what if you have a particle, a charge, the idea of a charge, a naked charge, point-like charge, which has zero rest mass, which in that sense is photon-like, but it's not a photon because it's a charge. So that zips around, and what is its kinetic energy and what's the potential energy? And that's where you can then apply basically when you have a two-dimensional, three, the star engines, you can distribute the energy over as many dimensions as your linear dimensions as you want. You will always arrive at the same thing. The energy equipartition theorem says, the energy of in that oscillator will be distributed over potential and over kinetic, and that this is where if that energy is distributed over these two energies, the potential and the kinetic energy, then we have a formula and we solve our mathematical problem, because the mathematical problem is basically that when you try to calculate the relativistic mass of using your formula and the Lorentz factor times the rest mass, but the rest mass is zero, and then your Lorentz factor is going to be infinity, basically. Why? Well, 1 divided by 1, the square root of 1 minus v squared divided by c squared, that gives 1 divided by 0, and in math, that's infinity. So you have this very weird undefined mathematical quantity, 0 defined by infinity. And so you can't solve that. But if you think about, you can solve it philosophically, saying like, half of the total energy, half of the mass of the electron, with using Einstein's mass-energy equivalence relationship, must be a relativistic energy of the, kinetic energy of the point-like charge. So that's and the other half is the electromagnetic, is the energy that is in the electromagnetic field, that it, because it's a ring current, it generates that. So we have half, and the mass of the electron as a whole must be distributed over the effective mass of that point-like charge and the relativistic mass it gets when it whizzes around. And that makes sense, because you can rewrite Einstein's mass-energy E as mc squared as saying like, the C, it's really an oscillator. It gives a beautiful explanation, a physical explanation of Einstein's mass-energy equivalence relationship. Is this C is really the orbital velocity of that point-like charge, and we know it's idealized. Maybe the trajectory will be more complicated. Like Schrödinger's equation gives us a very nice and shapes for elliptical orbitals and all kinds of shapes. But here, if we look at that, sort of reduce it to ring current, then that orbital velocity will, and it's actually also for an elliptical, if it would be a different orbital, is the radius vector times the radius times the orbital frequency, omega. So E is mc square. The energy must be proportional to, that's always the case from oscillators. That's also where this mass energy equivalence relation is actually sort of an oscillator equation. The energy in an oscillation is proportional to the square of the amplitude, which is the radius of our point-like charge as it zips around, and the square of the frequency, which is an orbital frequency, not a linear one here. And so c square, yeah, we can write it as a square times omega square. And then what is the factor of proportionality? Well, that's the mass factor in an oscillator model, and sorry, a mass factor, not a vector. And so in here, in this case, it's the effective mass, sorry, the effective mass of our point-like charge, which must be half of the electron mass or the proton mass, or whatever particle we're looking at. And so so basically there you have an energy, kinetic energy equation, which says, look, for a proton or an electron, it's mc squared, the mass of the electron proton, divided by 2. I probably lost you already, but it doesn't matter. I said I speak probably to very few people, but that's quite okay. Let us move on to the next slide. I think this is the basic model that I've been defending, and so in this paper actually I work it out for the proton, for an atom, for an electron, and so I want to present the basics of that. Yeah, maybe before I go there, so at the bottom I have these two formulas where the electron radius is h bar divided by mc, and you get it directly out of this beautiful Planck Einstein relation, which says that any oscillation is quantized. And how is it quantized? Well, the energy in the oscillation must be equal to h bar, Planck's quantum of action, times the frequency. And then we have the orbital velocity formula. C is, as I said, the radius times the orbital velocity. So then you can do the substitutions, and you beautifully get the immediately the electron radius, the Compton radius. A is h bar divided by mc. You can work it out. For the proton, we have a 4-factor, and this is what I want to explain in this video. I want to explain in the factor. This 4-factor is really why we think an electron is a 2-dimensional oscillation in a plane. A proton is spherical; it packs spherically in a nucleus. So you have a 4-factor there, which is just the same 4-factor that you have when you calculate the surface of a sphere. It's 4p r square versus the circumference of a circle. And that factor also pops up in other one when you go from a ring current to like a full disk structure. You have a factor 4. So when you sort of have look at the Gaussian factors in electromagnetic radiation, you go from 2 dimensions to 3 dimensions. You have a factor 4 pi. And so that 4-factor is really what distinguishes a spherical thing from just a planar thing, and I will talk about that because and in the paper I really argue, because you may say, well, that's kind of random, right? We have E as h bar times omega, and for proton we have 4 times h bar times omega. Why not 2 or 3 or 5 or 6 or whatever? This is the answer there is really like that 4-factor is really when you go from 2 dimensions to 3 in an oscillator in 3 dimensions. That's just a funny thing in math and geometry. And it gives us the proton radius, 4h bar divided by mc. I will talk more about that later. The thing why I put this figure here is already that you know, it's very complicated to sort of model, and I'm going to try to do that a bit using, I said there's no analytical solutions for these kind of things. If we model it like we have a force in the x direction, minus kx, a force in the y direction, minus k, the y coordinate of our point lag charge, and then a z direction, f subscript z is minus k z, then that becomes very complicated, and there's no analytical solution, so you really need to sort of work with graphing tools and stuff, and that this is something where I need to do probably a better job, but I already want to show you what happens in these things, and this is the electron model of basically I have to thank a bunch of Italian researchers called fusion research, where they say like, okay, you have that black thing, a ring current. If you add a lateral motion to it, this is really an electron in motion, and we have a ring current and some kind of potential field. This is going to start moving laterally. The thing is, this point lag charge, its velocity needs to be c, and so it means that if it no longer moves in one plane only, but also has, you know, the velocity has a lateral component, it moves sideways, then actually the radius of that oscillation needs to become smaller. That's just mathematically so. So the orbital velocity, once it's no longer, the motion is no longer confined to one plane, but there's a lateral component which you have in a three-dimensional oscillation. You know, it goes up and down, left and right, or front and back, and then, you know, it also goes left and right. Then you have indeed sort of this spiral-like structure that gets stretched, and you can think of some kind of, and that I need to work out, some kind of accordion, or I don't know, a trajectory that resembles, like, you know, when you wind yarn onto a ball or something. So it's a very funny, it's totally different ball game in terms of mathematically pinning down these equations of motion of our point lag charge. But this gives you a bit of a feeling of how you know, the point lag charge in a proton might be tittering around, you know, as a sort of accordion, and you know, the charge goes on the surface of a sort of follows a spherical orbital, but that's what's going to happen. I'm not going to do that in a previous. I showed there the relativistic invariance of the argument in the wave function. I note again that figure where, you know, this is the biggest mistake that and the biggest nonsense that you'll learn in any basic course is that mathematically, you know, spin matters. You know, the most of the models that you'll see sort of assume that you know, they're like spin zero, or there's no spin, and then you model particles very abstractly, and that doesn't make sense. You need to put in the spin from the start, and the thing is, you know, if you go from +1 to -1 and you use your imaginary unit as a rotation operator, then mathematically, yeah, Euler's number to the power plus I pi is equal to Euler's number minus I pi in math, but it's not in physics. It matters how you get there. And so you see a lot of rubbish in quantum mechanics where they say, oh, this is a common phase vector, and that gives rise to all kinds of weird, you know, 720 degree symmetries, you know, this distinction between bosons and fermions. You know, there's matter particles and there are light particles. There's electrons and protons, and you know, charged oscillations, and then there are photons and neutrinos, which we think have a different form factor, but a photon is a photon. It's not charged, and it's a linear oscillation, neutrino also. So that's why it moves in a line at the speed of light, while somehow, you know, a charge gets caught up in its own motion, in the electromagnetic field that it creates, and that's the beauty of this model, is that mass in the end is really charge in motion. I'm not going to talk more about this. Again, I did that in previous lectures, and I haven't started to talk about Yeah, the thing is, often I get this reproach like, oh, well, you know, your analysis is numerological only, or, you know, I'm wondering, like, you know, Feynman does a derivation of the size of an atom, and it's he himself calls it like, you know, this is just dimensional, but it's actually very precise. And he doesn't get this sort of complaint from other academics like, well, you know, that's numerologically, you know, only. So that's why I want to show his model, and then actually based on that, that will be for the next slide, show that there's a more general Planck Einstein relation. So we have E is h bar times omega, you know, that we can that we do have that factor n, you know, 1, 2, 3, 4, 5. And where it comes from, because it actually comes from this. This is one of the things that you know, I wonder why Feynman makes this so mysterious, and it's precise. He says, you know, look at an atomic system. We have an electron and a proton, right? We know that the energy must be kinetic half, and the other half must be potential energy. So the potential energy is, well, when you bring a positive and a negative charge together, we have this convention, you know, the zero energy level is, you know, at infinity, and so we bring the electron to the proton, and so we get energy. And the convention that we have is it's minus energy. Energy should be positive, but in any case, so this convention is that, you know, the proton and the electron will have less energy when they're together than when they are far away, because, you know, to remove the electron from the proton to a distance of infinity, well, you'll need energy. You need to pull it away because they attract each other. Why don't they sit on top of each other? Well, that's the Planck Einstein relation. We said that, you know, they're never going to sit on top of each other because they dance around each other. If they sit on top of each other, there is no energy. There is no energy. So the energy again is in that oscillation. The proton is very massive, and the electron goes around it, and that's where the energy is. And it's a charged oscillation. It's a current also, an electron that goes around a proton. So we have that potential energy, okay? And so the formula there is potential energy is minus the electron charge squared divided by 4 pi and then the electric constant and r. We can write it in all terms e square. That's another notation for the electron charge. Well, for QE squared divided by 4p electric constant. Then we don't have to bother with these constants and the 4 pi factor. That's a good thing and a bad thing at the same time. It makes the equations easier. At the same time, you do forget that we are talking a three-dimensional thing here. The formula for the kinetic energy, then, he says, well, that's just a non-relativistic, you'll recognize that, mv square divided by 2. I will talk about it actually, because that actually might be relativistically correct. When I see now m divided by 2, I immediately think, yeah, well, that's the effective mass. This kinetic energy is the effective mass of the point-like charge, that electron, times v square. But I'll come back to that. In any case, we have these two things, a formula for the kinetic energy and one for the potential energy. And so we write the total energy as mv squared divided by 2 on the kinetic energy minus e squared divided by r. And then, you know, mv squared divided by 2, we can write it as p squared, m squared times v squared divided by, well, we need to add an m, minus e squared divided by r. And then the big substitution there is that he substitutes p by h bar divided by r. That's really Heisenberg's uncertainty principle. I call it the certainty principle, that, you know, the change in the uncertainty on the momentum and the uncertainty on the distance is h bar. For me, it's, well, the momentum times the distance over a distance is h bar. H bar, Planck's quantum of action, you can write it either as a product, and we will do that also on the next slide, as some energy times a cycle time, or else what we are doing here as some kind of momentum. It's linear momentum, but in an orbital, what would call it, orbital momentum, times the circumference of the loop. Planck's quantum of action, and that's where I call Heisenberg's uncertainty principle, is that if you have an oscillation, that oscillation will obey the Planck Einstein law, and so Heisenberg's uncertainty principle is the Planck Einstein law. Is closely related, where the momentum times the distance, that will be equal to h bar, or the energy that is in the oscillation times the cycle time will also be equal to h bar. In any case, so that's the substitution he does there. The energy is then equal to h bar squared divided by 2m r squared minus the electron charge squared divided by r. And then what you're going to do is your reasoning is indeed sort of that electron and proton come together and are in this oscillation, in this dance, and this perpetuum mobile, and it's finely tuned, and it generates the field that keeps it in motion and keeps it going. So what will then the radius of the atom be? It must be a minimum, it must minimize the energy. That's what we said, taking into account that Planck-Einstein relation, or the Heisenberg's certainty principle, as I would call it. So math tells us that, okay, take the derivative. If you have a minimum, you're going to take the derivative with respect to the variable that is used for optimizing, for minimizing or maximizing the objective variable, I would say, which is the energy here. So you take that derivative, dE over dr, and then you calculate it all out, and then you arrive at the Bohr radius of an atom. So Feynman gets what he wants. So we can write that in terms of the fine structure constant, which is what we do here. And we know that the Bohr radius is actually the Compton radius divided by that fine structure constant. 1 over alpha is about, I think, 137. So the Bohr radius is 137 times, it's a lot, but it's not an awful lot, times the electron radius. We know that sort of an electron has like 3 radii. I would say this Bohr radius, the radius of an electron orbital in an atomic or molecular system, and it has its own Compton radius. When a photon comes, messes with this electromagnetic field that is generated by the ring current, there's a scattering radius, that's the Compton radius, and now we have finally the radius of that point-like charge, which because there is this so-called anomaly in the magnetic moment and whatever, it's not an anomaly at all. This point-like charge inside of an electron does have a radius of its own, and so that fine structure constant relates these 3 radii. The only thing I want to say about this is that this is sort of a dimensional analysis, maybe, or it's not numerology. It's quite precise, and it gives you the base state. One electron, the lowest electron orbital. When an atom gets excited, then the physical action will not be h bar, but 2 times h bar or 3 times h bar. And this is what I'm going to show, where this Planck Einstein relation in the energy is h bar times an orbital frequency becomes indeed 2 times h bar times an orbital frequency, so 3 times. I just want to say one more thing. I said if you do substitute his non-relativistic kinetic energy formula by replacing the electron mass divided by 2 by the effective mass, then you get a kinetic energy is the effective mass times v squared. And that gives you, that reminds us of, there's various derivations of the relativistic mass formula. That formula that I put here, the relativistic mass is the rest mass, m0 divided by the square root of 1 minus v squared c squared. So it's the Lorentz factor times the rest mass. Well, that formula, you can derive it from a relativistic formula that is correct. P squared will always be equal to m squared v squared, obviously, and that's the definition of momentum. And you can show. I'll refer to Feynman that, or look at the paper, the reference is there. You can show that's always equal to m squared, total mass squared, times c squared minus the square of the rest mass times c squared. And so that's why I think actually that a finite model, although he calls it non-relativistic, it's kind of weird that he gets the exact right values out of a non-relativistic model. But that's a different discussion. I just want to show that these derivations make sense and they're precise, and they're not numerology at all. There's a model that underlies these things, physical principles. This is where I want to generalize then, and I'm doing the Bohr atom. You don't learn that anymore in quantum mechanics. You can say, oh, it's circular orbitals. The Bohr model has many things that are not correct, but it does give you the basic quantum numbers, the energy levels. And if you, I mean, the nice thing about the Bohr model is that it's very mechanical. You can really calculate the orbital 1. The principal quantum number n there, 1, 2, 3, 4. The physical action in the first, second, third orbital will indeed be n times h, n times Planck's quantum of action. And the energy of the second, third, when you build up your atom model, and you have not only one electron, but an electron pair, and then you go to the next shell, subshell, then the energy will be equal to, that's the formula you get. You can really calculate it from these mechanical formulas for using the radius, using this classical velocity, because in an atom, an electron, I said it has a mass, an electron, so the velocities of the electron in an atomic orbital, they're actually non-relativistic. They're a fraction of the speed of light, and a fraction that is not very large, small fraction. It's given by 1 over n times the fine structure constant again, so times c, so 0.0071 divided by n. So you see you have very small fractions for this classical velocity, and you can combine that. The orbital frequency is given by the velocity, of course, divided by the radius, and so you write, and what you see there is this Rydberg energy that pops up, or the Rydberg frequency. You can calculate then the magnetic moment mu for each orbital 1, 2, 3, 4 using a very classical formula again. The current E times pi times r square. So that's the formula for a magnetic moment generated by a ring current, and you get that QE, the electron charge divided by 2m and h. The substitution. I calculated G factor there, but I'm probably not gonna come back on it. The G factor is a weird thing. I think it confuses a lot of things. It depends on the G factor is supposed to be a dimensionless number, right? That you have the gyromagnetic ratio, the angular momentum Ln, which is there, and then the magnetic moment. So mu, the magnetic moment divided by the angular momentum, that gives you the gyromagnetic ratio. And then the quantum physicists, they rewrite that, so to speak, by choosing a unit, the Bohr magneton, which is QE divided by 2m. And why not Q divided by m? Why that 1 over 2 factor? So that's already something random. There's a magneton that you use. Do you put a 1 over 2 factor, or you don't put one? If you put it, and then it's sort of, your angular momentum, do you only count the angular momentum, the kinetic energy, as the charge whizzes around? Of course, the field must have also some angular mass, a moment of inertia. So the G factor is a very confusing concept, and depends really, you can, here I get the G factor 1. I will show you I get a classical one. Do I show here? No, maybe the next one. What I want to go back to these equations, I put on the left hand side there, sorry, the right hand side, the nth energy level. So that's minus 1 over n square times the Rydberg energy, and then the orbital frequency, we have that formula as well. And you can see there I arrive at what I wanted to show you, is that for these various electron orbitals, you get a formula that equals the energy is n times h bar times the orbital frequency. you'll see, okay, there's a factor 2 there. But think again, think about the implied energy concept, our particle modeling here and these mechanical equations. We only we're really talking kinetic energy, velocities of an electron, and that has an effective mass, and so the total energy should include the whole energy of the electron, electromagnetic field, including the electromagnetic field. Sorry, I'm covering the text here, that is being generated by the oscillating charge, because that field is what keeps the oscillation going. So then that factor 1/2 disappears, and we have what I would call sort of a generalized Planck Einstein relation, which says the energy is h bar times an orbital frequency times a factor n, which is your principal quantum number 1, 2, 3, 4. So there's nothing mysterious about using a 4 factor in our energy, the Planck Einstein relation, for when we are going to try to model a proton as an oscillation in 3 dimensions. There's nothing weird about that. The next thing then here is what I said. So we have that general E as n times h, Planck's quantum of action, times the frequency, and when we write it in reduced form, we get h bar times an orbital frequency. So this n is really again a form factor related to the particularities of the electron orbital. And so when you apply the Planck Einstein relation to an electron or a proton, it's no surprise you also get such form factor, which is 1 for an electron, and we think it's 4 for a proton. Why? Because this 4 is the form factor that you have in formulas like the ones I write here. The surface of a sphere, you get a factor 4. If sort of that charge is not a ring current in one plane, but goes around, then when we measure the magnetic moment, it will look like a solid disk, and you have a 1/4 factor there. So you have a Gaussian 4p factor that pops up in almost all equations when you generalize a 1 or 2 dimensional analysis to an analysis in 3 dimensions. Yeah, I wrote that actually, that potential electromagnetic energy formula that I already used. So and then for the rest, I'm not going to say too much about it. I said these quantities, when I use the Bohr magneton and classical quantities, h/2 for the angular momentum, then I get a g factor of 2, which is what you will see. You'll say, well, it's not exactly 2. We have that anomaly. Here I want to be very clear. You see that picture there. When you think of a charged oscillation, really a point-like charge in a ring current, or spinning around in 3 dimension, actually it is not infinitesimally small. It is very small, but the anomaly is of the order of the fine structure constant itself. So it's 0.007. So for me it's very clear that it must be related to the small but non-zero dimension of that point-like charge that is whizzing around, and that's why then you need to distinguish the mathematical radius, the center of the oscillation, and then the center of that point-like charge. But if you know that point-like charge has some dimension of its own, then if it goes around, part of it will be outside of that mathematical part of the charge will be outside of the mathematical, or the ideal, how we call it, the mathematical radius of that thing. So you'll have an effective radius that is a bit difficult. That's where you have these these loops in quantum field theory. For me, is just like when you model that, you see that you need to do an iteration. You have in the first iteration slightly different effective rates, a slight difference with the mathematical ideal radius, when you really think of a point-like charge having no dimension whatsoever, and an effective radius, and then that's sort of where that then determines the current is a little bit different than the ideal mathematical current that you would have. And so that's where the anomaly pops up. And that's what I put in the very first lecture. I show that the anomaly is not an anomaly at all. It shows that we are really modeling something realistic here. And that, you know, point-like charge with no dimension, 0 dimension, that doesn't exist. Things that have no dimension whatsoever. I don't know why mainstream quantum physicists have so much trouble understanding that. Apparently, something that has no dimension whatsoever, you know, doesn't exist. We say, well, photons don't have any dimension. They're really point-like. Yeah, that's true. You know, that's really like a point-like electromagnetic field vector traveling through space. But at the same time, that's probably the smallest dimension we can imagine. Photon interference experiments do show that there is an interaction radius there as well. So the photon probably has a size. It's too small to measure. But the fact that they interact with each other means that, yeah, they must have some kind of interaction radius as well. So even photons are probably the smallest thing that we can imagine. I think, you know, 100 years from now or 50 years from now, you will see that these, and I don't know why they do it now. I looked at the core data. There's a lot of experiments, photons, you know, that get fired into each other. Why don't they calculate some kind of at least a rough measure of what would be, you know, the size of a photon? But that's a digression. I want to talk about matter particles only here. And that's what I'm doing. I'm almost done. 45 minutes. I'm doing well. I want to keep it under 1 hour. Yeah, this is the funny thing what I said about the G factor. You know the G factor, or you don't know that, but the G factor, if you look at code data, is about 5.5857. That's a weird value. Let me first give you a theoretical value, because if you use, this is the other thing with the G factor, you would think like if you want to reduce the gyromagnetic ratio to a dimensionless number that sort of gives you information about, you know, the shape of that thing, because that's what the gyromagnetic ratio should tell us. It is like, okay, we have a very different magnetic moment and a very different angular momentum. I mean, the ratio between the two is very different. So what's the reason behind? The reason must be that their shapes are very different. You know, proton is not an electron. That the densities are very different. A proton is very dense as compared to an electron. So all that stuff, and that's the thing where you say like, okay, then use, you know, one unit. Use the electron mass divided, sorry, the electron charge divided by the electron mass. You know, QE divided by ME, or use the Bohr magneton where you have that factor 2 in it. But no, so we use a nuclear magneton. Which looks the same. I made a mistake there. Nuclear magneton is, oh no, it's not a mistake. It's the electron charge, because that's the same as the proton charge, well, with a different sign, and divided by the mass, 2 times the mass. We have the 1/2 factor. Why is there? For historical reasons. Multiplied by h bar. So if you calculate that, actually, the G factor, the theoretical one, is you get a G factor of 4. Now you will say you're totally off. I'm not, because this is something funny, and in the sense that we also know, like when you try to measure a magnetic moment, you will measure it in a magnetic field. It will be a magnetic moment that is there, and you will, you know, in a penning trap, you will measure that. The thing is, you will be applying an electromagnetic field to it, and it will precess. It's like the precession of the Earth in a gravitational field, and that's where you get a factor, a square root of 2 or a square root of 3 or other square root factors, and as I showed that in the paper, that also gives you information. We need to apply a square root factor here, and then you get a value which is corrected for that precession, and that's what I do here. So I use my radius formula, I insert a factor 2, which is a factor for a spin 1 particle, because it's a three-dimensional oscillation, but still is kind of like of a ring current. And I get something that is very close, but, well, very close. I get 5.65685, while the Kodada value is 5.8. So that's actually a difference of about 1.2%. Which is more than the fine structure constant. So we think actually, and this is the thing that probably over the next 20-30 years, you know, they will, because already measuring the radius of a proton, because it's so small, you know, the systemic error and the standard error is a lot bigger than the measurements for an electron. But you do see an anomaly, and this is going to be interesting. Probably now that the proton radius is solved and we have very precise measurement, is that we are going to probably see what happened with the electron as sort of theorists and experimentalists, you know, catching up with each other and calculating it to an ever finer degree. My gut instinct tells me that we're not going to have what we have for the electron, is that the point-like charge is basically alpha times the electron radius as a whole. It might be a different size, I would say, a larger point-like charge in a proton. Why am I saying that? Because in the end, is you know, an electron is an electron and a proton is a proton. If sort of the nature really of the charges would be exactly the same, then the proton would be an anti-electron, would be a positron. It would not be a proton. So that this is where I think the, you know, electrons and protons, they're like two particles. You can think of them as sort of given by nature, and so I don't think that I don't think that the proton is like a positively charged electron with a different structure. No, if it has, well, it is. It has a different structure. As I said, it's more dense, it's three-dimensional oscillation, but it's also where probably, you know, I said a proton is not some kind of three-dimensional version of a positron. I think that doesn't make sense. Otherwise, you know, you would. So probably that's going to be interesting to see. But you know, that's for future generations probably to figure out. I'm not sure if it warrants like huge investments in even more expensive scientific equipment, but physicists will say yes. I don't know. Maybe that money could be better spent on you know, poverty reduction in our societies or something. But that's a philosophical remark. In any case, that's so that's kind of open there. That's where the uncertainties are large in the current field, and I think I'm gonna move on. Yeah, I still have 8 minutes left because I want to close like in 1 hour. Feynman wrote an intriguing epilogue to his lectures, and I want to read it out for you because it's also, I said, it's my last lecture. I'm tired of it. I don't want to, you know, I put a lot of effort in these things. I'm happy. I have a feeling I understand reality, so it has been very gratifying for me. I will also say that one of the reasons why I'm sharing these things is I really got frustrated in doing what you probably are doing, you know, following sort of online courses and reading about this and then asking very basic questions. And I said at the X course, I ask these questions, I present my models and say, oh, shut up and calculate. You know, well, nobody really understands and this and that. And this is where I think I want to quote Feynman, because I think he also, he did his best now with his lectures. He wanted to actually bring more bright students back to the field of physics because everybody was leaving, you know, for engineering and other studies, and which I think is correct, because I think science, that was the title of my previous lecture, The End of Physics. As a science, we're pretty well done. We know everything, we know how it works, and what is left indeed is engineering. So, but having said that, so I would not recommend you go for a PhD in physics or for physics studies themselves. And I have a nephew who also sort of dropped out very disappointedly, and I must say I would not get through a basic course of quantum mechanics, because I would challenge the professor, saying like, you know, these things, sorry, all that hocus pocus. Quantum field theory. Yes, fields are quantized, of course they are, but you know, the momentum gets ferried around from here to there by an infinitely small field particle. You know, what the heck? We have photons, electrons, protons. That's it, and we have models for them, and so quantum chromodynamics is completely crazy. But let me read it out, because it's sort of my farewell. I've been talking to you for 2 years. I think I started my writing in 2021, and I produced videos. So yeah, 2-3 years. So now I'm going to quit. In some ways, I would like to apologize, and other ways not. I guess the same. I hope, I know that 2 or 3 dozen of you have been able to follow everything with great excitement. I don't think I have 2 or 3 dozen people, although I get nice mails, but I also get a lot of nasty reactions. But the very few that have followed everything with great excitement, I would say thank you. That's for you. I did these videos. The powers of instruction are of very little efficacy, except in those happy circumstances in which they are practically superfluous. I find that a lot. You know, I try to explain things, but either you understand it or you don't. For the others, if I have made you hate the subject, I'm sorry. I'm probably, that's not, I never taught elementary physics before, that's for sure. I hope that I haven't caused a serious trouble to you. I don't think so. That you do not leave this exciting business. I would say leave it if you're happy with this explanation. I hope that someone else can teach you in a way that doesn't give you indigestion, and that you will find someday that after all it isn't as horrible as it looks. That is for sure. After you know, struggling with all these things, it is not as horrible as it looks. It is actually all quite self-explanatory, and I hope I can give you that feeling as well. Finally, may I add that the main purpose of my teaching has not been to prepare you for some examination, and it was not even to prepare you to serve industry or the military. So for what was it? And that's actually, I think, my drive as well. I wanted most to give you some appreciation of the wonderful world and the physicist's way of looking at it, which I believe is a major part of the true culture of modern times. He wrote it in 1963. And it is what has drawn me into this field, and which is why I'm marketing my papers a bit, because I do believe indeed sort of you know, who does not want to know about these things? Who does not want to understand? It's like yeah, living in a wonderful world indeed, and not even trying to understand it. For the rest, then he finishes, perhaps you will not only have some appreciation of this culture, it's even possible that you may want to join in the greatest adventure that the human mind has ever begun. There I would say Feynman is also the father of nanotechnology, and it's indeed true, all the wonderful things that are happening in molecular biology, medicine, engineering, nanotechnology, and computers, the miniaturization. It's because the guys like Feynman envisioned that and described it. So that's where, with all my criticism on Richard Feynman mystifying stuff too much, I must say he is a great bridge. I think in some of his lectures he's sort of hoping, yeah, that we get it. I think I get it. I think he was a Nobel Prize winner himself with Gell-Mann. He had a lot of difficulties. I honestly don't think he believed he had a parton theory, quark gluons, the way he speaks about it in his lectures. I looked at the videos. I think he also deep inside says, like, you know, we've gone off track there. But that's it. That's it for my very last appearance on this topic on YouTube. I don't know how many people will watch this to the end. Those who do, thank you very much. Like it and share, because after all, you know, with all the effort I put in it, I do want to have a few reads and see my statistics on the ResearchGate go up a little bit, so that this open science project of mine hasn't been too futile. I wish you a great evening, and I will stop here. Thanks.